Homework 20, hypothesis test for mu, sigma known, video 5. Testing mu, the p-value approach. Full disclosure, I prefer the critical value approach to the p-value approach. However, in certain contexts, the p-value approach is easier to execute depending upon what information you have in advance. I'm thinking specifically in the Statistics 2 class that I teach at UT Tyler, where in the context of a hypothesis test, we're told the p-value up front, which makes the hypothesis test almost over as soon as it starts. In these problems, however, we will not be given the p-value. I'll explain what a p-value is and how to find it and what to do with it. But previously, this is the tip was $5, no it's not example a couple of videos ago. So just to summarize what happened real quick, our hypotheses were null is mu equals 5, alternative is mu is less than 5, because the sample suggested that. Our critical region was the left tail, and the critical value was z equals negative 1.65. When we calculated our test statistic, it ended up being negative 0.1865, which was to the left of center, but not far enough left to cross over into the critical region. And so we did not reject the null hypothesis. Do not reject the null hypothesis. It's important when you're stating your conclusion that you say the null hypothesis, because if you just say do not reject, don't reject what? The null or the alternative. So it's important to say do not reject the null hypothesis. Well, what's the p-value approach? Well, if you recall from the first video, the p-value is the probability of the sample occurring. And in that first video, it actually talked about the probability of a sample being unlikely. Basically, when you set up the significance level, oh, I'm sorry, I didn't define the p-value in the first video. I defined the significance level. I wish I could erase that last 30 seconds, but I'm not starting over. The significance level is the smallest probability that's tolerable when you're testing a population claim based on the, let me try this again. The significance level is the largest acceptable probability of a sample occurring, assuming a null hypothesis is true. So in other words, when we said, and I didn't write it here, that the significance level was 5%, what we're basically saying is we're not going to reject this unless something happens whose probability is 5% or less. Because if something occurs whose probability is 5% or less, that is highly unlikely, given us reason to think that the middle of this is not what we claim it is. So it sets up the boundary, if you will, for a probability of a sample occurring. Now, did we actually figure out the probability that the sample of 87 tips would give us $4.50? No, we just calculated its z-score. But from a z-score, we can calculate a probability and see what that means. So in this example, the question we can ask is, what is the probability? What is the probability that X bar was $4.50 when the sample size was 87? The claimed mean was 5, and the sample standard deviation was 25. And if the probability of this thing happening is less than 5%, that's so unlikely that our evidence is strong enough to reject this. But we never actually answer that probability. That probability is called the p-value. So, the p-value is the probability, and that's what the p in p-value stands for, that X bar was less than or equal to $4.50. Now, why did I say less than or equal to? First off, when you're doing a probability involving X bars or any continuous value, you can't say equal because the probability of a continuous variable being an exact value is 0. But if our sample mean was less than or equal to $4.50, that is strong evidence that we need to reject the null hypothesis, saying, no, it's $5. No, we got something $4.50 or less. If we wanted to calculate this probability, we could draw a curve. The x bar's means is mu, so $5 is there. $4.50 is to the left of this, and the probability would match this area. But in previous videos, we learned that the way to calculate this area is to convert this to a z. But did we not already do that? We did it over here. We converted the x bar to a z. So the probability that the sample would give us 450 or less is the same as the probability of z being less than or equal to negative 0.1865. Now here's where our z-chart has its limitations. These z's in our z-chart only have 2 decimal places. So we need to round this to 2 decimal places. So the probability that z is less than or equal to negative 0.19 is what this would round to. And then we would just get out the z-chart. Don't worry, in a minute I'm going to summarize what's going on here. Negative 0.19. The probability, oops, wrong place. I looked up negative 1.90. Negative 0.19. That probability is 0.4247. So what does this mean? This means in the context of the problem, if our sample gave us a $4.50 mean tip when we took 87 tips to average, but we're saying that the population mean is actually 5, and our population standard deviation is 25, then the probability of our x bar being $4.50 or less is about 42%. If something is likely to happen 42% of the time, that's not unlikely. That's almost expected to happen half the time, 50%. So the probability of our sample being this or worse, in this case worse means even less, was pretty big. That's not very unusual. If it were less than 5%, that would be an issue. So the p-value approach goes something like this. You don't come up with a critical value because you don't need it. All you need is the significance level. However, you do have to calculate your test statistic and then find the probability associated with it. If that probability is too small, then you reject the null hypothesis. So in the next video, I'm going to summarize everything that was just said, but the premise behind it is the p-value is the probability that your sample or worse occurred. In this case, worse means even less than $4.50. And if that probability is too small, then your event is unlikely and your null hypothesis is incorrect. All right, I'll summarize it nice and clean in the next video, step by step.